As friends, in the last lecture 1, I have defined the stability of the critical points when the roots are distinct, that is case 1, and also defined the subcases of A, 1A, 1B and 1C. Now we start the subcase 1D. Okay, here if one root, if one root, yes, is 0 and other root is non-zero, let us suppose that lambda 1 is equal to 0 and lambda 2 is less than 0. That is the case y1 from the earlier. y1 is equal to c1 e to the power lambda 1t. Yes, and y2 this is equal to again is equal to c2 e to the power lambda 2t here. Here you see that as t tends to infinity, this y1 t tends to infinity, you see that y1 is equal to and y1 and y2, these are y1 is equal to, yes, for if lambda 1 is 0, then you see that is equal to c. Yes, t tends to y2 is equal to, this become y2 tends to 0 as t tends to infinity. Yes, for lambda 1 is 0, then y1 is c and lambda 2 is less than 0, that is any negative, then negative is here, then this is negative. Yes, in this case, yes, in this case, origin is stable proper node. Yes, proper node is clear. And the phase portrait, which is defined as phase portrait, yes, which is defined as y1 is here and y2 is here and there is a stable, that is the case like that. Yes, and all the orbits tends to origin. Yes, all the orbits tends to origin. You can see here from this phase portrait, you can see like that. Okay, yes, this is the case when lambda 1 is 0 and lambda 2, this is less than 0. And similarly for the case when lambda 1 is here is for lambda 1, similarly, yes, similarly you see if for the same for lambda 1 which is equal to 0 and lambda 2 which is greater than 0, then you see here if lambda 1 0, then again y1 is equal to c1, but if lambda 2 which is greater than 0, then you see here this tends to infinity. Yes, therefore you see that the phase portrait y2 tends to y1 tends to c1, but y2 tends to infinity, that is all orbits goes away from the path. Yes, and the phase portrait which is defined as like that y1 and y2, and the phase portrait in that case is defined as, yes, all the orbits goes away from the origin. Yes, like that. Okay, all the orbits goes away from the origin. Yes, and the origin is, so you can say that origin Yes, origin is unstable. Yes, origin is unstable proper node. Yes, proper nodes. Clear? And this is the case when lambda 1 is 0 and lambda 2 is greater than 0. So we have defined for the case 1 when the rules are districts, case subcase 1, subcase A, B, C and D up to. Okay. Now we start the case 2. Yes. Case 2, that is, now we start the case 2. Yes. Case 2. Here we suppose that the roots are double or the repeated roots. Yes. Double roots. Okay. Double roots. Or you can say that the roots are repeated, that is you have 2, 2, 3, 3, 4, 4 or minus 2, minus 3, minus 3, minus 4, minus 4 like that. Okay. Then we define the phase when the roots lambda 1 and lambda 2 are equal, that is like that. Lambda 1, you can say that this is equal to lambda 2. Okay. In this case, yes, in this case, matrix D is given by D, which is defined this one, lambda 1, 1, 0, lambda 2, and also D is defined as lambda 1, 0, 0 and lambda 2. The D in this case, for lambda 1, lambda 2 is equal. Here, if lambda 1 is equal to lambda 2, then this is again can be written as, D can be written as lambda 1, 1, 0, lambda 1, and again this can be written as D is equal to lambda 1, 0, 0 and lambda 1. Yes, this is the case when the roots, for the linearly dependent characteristic vectors. Yes, characteristic vectors. Yes, and that is the case D is for the linearly independent characteristic vectors. Okay. Now we define for both the cases roots, nature of the roots for linearly dependent and also for the linearly independent. Yes, now we can say that define the subcase. Yes, subcase. Yes, 2b in this case, 2a and also for 2b. Linearly for dependent case, linearly dependent characteristic vectors. Okay, then y dash is equal to dy and y and d is defined as operating, d is the here is like that, so operating as y1 y2, so you can say that y1 is defined as y1 y2. Yes, y dash, this is again is equal to y1 dash and similarly y2 dash. Yes, and d is equal to lambda 1, 1, 0, lambda 1 and similarly y is y1 y2. Operating this here, then we get dy1 by dt is equal to lambda 1 y1 plus for y1, y2 again is y1. Yes, y2 is here, y1, y2. Yes, you can say that if you start. And similarly for d, y2 by dt. Yes, this can be written as lambda 1 y2. Yes, on integrating this, if you integrating this, then you can say that y1, this is equal to this linear differential equation. Now you can get the result tc2 plus c1 e to the power lambda 1t. Yes, and similarly y2, you can integrating this, you get c2 e to the power lambda 1t. Yes. Now we discuss the case when lambda 1 is 0 or less than 0. Now we define the case. Yes. Now, if lambda 1 is less than 0, thus from the cases you have defined as thus the critical points 0, 0 of the system is asymptotically stable improper node. And the phase portrait is given by like that. Yes, like that. Yes, y1 is here and y2 is here, and the system is stable. That is, the phase portrait is defined like that. Yes, y1 all tends to y1 like that. Yes. Okay. Yes, this is the case. Yes, here you can discuss y1 is equal less than 0. You can say from here y1 is t to the power 0. Yes, less than, then this is tends to 0. That is, you get the stability of the point. Okay. Now, if lambda 1 is greater than 0, in this case the points are, we get the infinity at t tends to infinity. That is, in this case the orbit of the path moves away from the origin. Yes, away from the origin. And the origin is unstable improper node. And the phase portrait, similarly, we can define as phase portrait is here. These are, yes, away from the orbit. Yes, away from the origin. Yes, you can see that from this. And now for the next case, subcase B. Yes, subcase B, subcase 2b. Yes, subcase 2b, which is, you can say that for the linearly independent vectors, in dependent vector. Okay, in this case, yes, in this case, y dash, similarly for the last earlier case, y dash is equal to dy, but d is here is d is lambda 1 0 0 lambda 1 like that. Okay, and y dash is the same y1 y2, so we get y1 dash is equal to lambda 1 y1, and similarly y2 dash is again is equal to lambda 1 y2. Now integrating this, we get y1 is equal to c1 e to the power lambda 1 t, yes, and similarly y2, this is again is equal to c2 e to the power lambda 2 t. For this case, similarly for the here, as we discuss here, lambda 1 is less than 0 and lambda 1 is greater than 0. Similarly, we discuss the case if lambda 1 is less than 0, then you say that lambda 1 is less than, there this is negative, therefore the y1 tends to infinity, this tends to 0. Okay, as t tends to infinity, therefore you see that, therefore you say that the critical points 0 0 asymptotically is stable, yes, a stable proper node, yes. Okay, and the phase portrait, which is defined like that, y1 is here and y2 is here, yes, similarly, and these are the asymptotically stable, that is the phase portrait. These are the defined like that, yes, that's the origin like that. Okay, yes, okay, like that. Now when this is the case for the critical points are asymptotically stable for the, yes, proper node, and when lambda 1 is greater than 0, then get lambda 1 is greater than 0, that is y1 tends to infinity, as t tends to infinity here is, then you say that then the solution of the system, then the solution of the system moving away from origin, and then critical point 0 0 is unstable, and phase portrait is given by, yes, is given by the proper node, that is the critical points, that is the critical points 0 0 is asymptotically unstable, yes, unstable proper node. Okay, and the phase portrait, which is defined like that. Yes, you can see that these are away from the origin. That is, the face portrait is defined like that. Yes, this one, no, here is sign is here, like that. Yes, this is the case. Here we define these are the case. Now, okay, now in the next case I have defined, in the next video I have defined the case third, that is the roots are complex. Okay, okay, thank you.